Greetings and welcome back. Today we'll be looking at organic oxidation reactions. You may recall that in the previous video we looked at how carbonyls could be reduced to alcohols by the addition of bonds to hydrogen. In this video we'll be looking at how alcohols can be converted to carbonyls by removing bonds to hydrogen or adding additional bonds to oxygen. This is called an oxidation reaction, and we'll have just a few of them to consider. The most selective way to convert an alcohol into a carbonyl involves removing both the hydrogen attached to the oxygen and the hydrogen attached to the carbon as well. So you'll remove both of those hydrogens. And the best way that we have to do that, and best is a relative word, but the most selective way to do this is with chromic acid, H2CrO4. Similarly to KMnO4, which is potassium permanganate, this is a metal oxide, and it is used to oxidize this all the way down. Again, there's a mechanism known for this, or at least suspected for this, that we can go through if you'd like. But all of these chromium reagents are very good oxidizers, very strong oxidizers. In fact, chromic acid is such a strong oxidizer that we cannot use it and store it. Well, we cannot store it, and therefore we have to make it in a pot. There's two different ways of making it. One is from CrO3 plus acid in water, and the second is from sodium dichromate, Na2Cr2O7 plus water, or aqueous acid. And so in a pot we can produce chromic acid, and then we can use it to oxidize our alcohols all the way to carboxylic acids. And so this will only work if you have a hydrogen and an OH on the same carbon. So therefore, if you were to start with a tertiary alcohol, no reduction can be done. No oxidation can be done, because there is no H to remove, and so therefore that guy is at its full oxidation state already. If you have a secondary alcohol, that is to say an OH attached to a carbon with two carbons and one hydrogen, using our chromic acid or our CrO3 in aqueous acid would oxidize by removing this hydrogen, and we would convert it all the way to a ketone. If you have a primary alcohol, there are two hydrogens, and therefore what can happen is that using chromic acid, H plus aqueous, would oxidize this all the way to a carboxylic acid, because there are two hydrogens that can be removed, and it would oxidize it all the way to a carboxylic acid by removing both of those hydrogens and replacing them both with bonds to oxygen. An alternative method for these oxidations involves KMnO4 instead. KMnO4 will do all of these, or perform all of these oxidations in the exact same way, except that KMnO4, as we've seen earlier in this course, can react with other functional groups, including alkenes. The chromic acid, or these chromium compounds, cannot react in the exact same way, and therefore the chromium reagents are much more selective. The KMnO4 will do a lot more kind of side reactions. So what would the benefit be of using KMnO4? Well, actually there's a number of benefits. It's cheaper, which is nice. It's also, in terms of its byproducts, far less toxic to the atmosphere, or just really anything. So it's more environmentally friendly and also less toxic. But the trade-off is that it's less selective. So if you only have one functional group that you'd like to oxidize, KMnO4 tends to be a much better choice. However, if you have multiple functional groups in your molecule and you just want to oxidize the alcohol, the chromium can be used instead. As a fun side note, chromium will change its oxidation state over the course of this reaction, which also changes its color. The fact that that chromium changes its color can be used as a test for alcohols, because if there is no alcohol, there is no oxidation that can be done by chromic acid. So therefore, this reaction is actually used in breathalyzers to be able to sense whether or not there is an alcohol present in somebody's breath. You may have noticed one limitation of these reactions in terms of oxidation is that we can only, using chromic acid, completely convert our primary alcohol all the way to a carboxylic acid. In other words, this one right here, this primary alcohol, is doubly oxidized. Part of the reason that that occurs is that the OH and H are oxidized to an aldehyde, and then that aldehyde can be converted into a hydrate, which then has an OH and an H and can be oxidized again all the way down to the carboxylic acid. If, however, we want to stop after one oxidation, we can use a compound called pyridinium chlorochromate, which is another chromic acid reagent. However, being attached to pyridinium, it is soluble in dichloromethane instead, or other organic solvents. Because you wouldn't add any water, you would not convert the aldehyde product into a hydrate, and therefore there would be no second oxidation. So therefore, using chromic acid, we can oxidize a secondary alcohol to a ketone. We can oxidize a primary alcohol all the way to a carboxylic acid. But if we want to turn a primary alcohol into an aldehyde and stop there, we would use pyridinium chlorochromate instead. So you'll notice that all of these are merely functional group interconversions. None of them involve the conversion of an alcohol into some other functional group while adding carbons. So therefore, all of these just convert one functional group into another functional group, maintaining the exact same number of carbons. So I would write these down on your flow chart with your functional group interconversions, but that's what these are. We've done all of these reactions in reverse, and now we're doing them in this direction as well. We can both reduce and oxidize quite readily without fooling with other functional groups in our molecules. So these are reagents to know, reactions to know, and please bring any questions you have to class. Thank you very much, and I'll see you soon.